Okay, we're recording. And we're going to take a look at this problem that I gave people yesterday. And the problem is find, there we go, find the derivative of this implicitly defined equation and find the equation of the tangent when x is 1. So all that we did yesterday, as far as we got, was we figured out that, well, if x is 1, we can figure out that y is 1. And for those of you who haven't done grade 12 math yet, this is going to happen. So we plugged in a 1 to these x's here. Oops, that's not an x. To those two x's. And that gave us this equation here. And I simplified it to this, but can I factor that? And the answer is, well, no, that doesn't really factor. So the only real strategy we give you here in basic high school pre-calculus math is that you have to kind of try guessing and checking it. It turns out that the first number I tried, y is 1, worked just nicely. 1 makes that a 0. Therefore, y equals 1 is a solution for that. So that means that I have the 0.11. If this had been a question where it didn't factor or a whole number integer was not something that would give me the answer for 0 when I plugged it in for y, then I'd need more advanced techniques. There is something, just like in grade 11 you learned a quadratic formula, there is a cubic formula that they teach you in, I think, like, they don't even teach it to you in first year university. I think it'd be like second or third year number theory. So for the most part, if you really wanted to solve something like this and you could not figure out by guessing and checking, or guessing and checking won't help you because it's an irrational answer or something, you'd actually solve it by plugging it into a program like Desmos or a graphing calculator and finding out where the zeros are. It's a cubic. Those of you who've done grade 12 know that that means it changes directions twice. So it could have up to 3 solutions, right? It could go 1, 2, 3. There could be 3 x-intercepts. I found one. It happens at when x is 1 and y is 1, or sorry, when x is 1, y is 1. So, or sorry, this has, of course, the solution of 1, which means that the original function, right, or not even a function, sorry, the original curve is that. That means that the 0.11 is on that curve. This curve here may not have any x-intercepts or y-intercepts at all. I mean, it could be just some sort of curve that exists out there like that. We don't really know, okay? Unless we graph it, of course, and we'll graph it in a minute. Okay, getting back here. That was, okay, I'm just going to check that noise just to see if that was good news about things. Oh, no, it's not good news. Access to our website, network file sharing, Mayette. That's our attendance program we used before EDSB. Access to Office 365, email, and Teams, and some internet appears to still function. So we're just going to try to limp through the day with what we got, I guess. All right, and I'll wait like two more minutes or so, and I'll run attendance. But as of right now, we have 24, 25, 26, 27, 28, 29, 30. We have 30 people here. That's almost the whole class. That's only a few people not here. Okay. All right. Any questions so far? Anybody not understand how I got to the point where, okay, I finally know a point on this curve? You know what I've been saying? We're going to use Desmos for this, so let's just go look at Desmos. Let's look at the curve before we start playing with the differentiation. So going to Desmos. Okay, I don't know if this is going to work. Internet. Now let's see. Okay, Pembina Trails is going to fail, but I want to actually just type in Desmos. Hey, come on, Desmos. Hey, Desmos works. Oh, it even remembered to log me in. I didn't log out when I left it. Excellent. So I think I still have, oh, maybe I don't have the graph saved. This is that lemon skate problem from the other day. There it is. That's the one we're looking at right now, isn't it? Not the lemon skate. This guy. So this is our curve, and we just found that, of course, the curve does have the point, open a brackets, 1, comma, where's comma? Comma, 1, as as a point, and we would like to know the tangent at that point. So that's as far as we've gotten. That's what we know, okay? And again, if I could not find that 1 point, if there, if the algebra had failed me, or there was absolutely no place on this curve where there was an actual sort of integer xy value that I could find using my algebra tricks, I would go straight to this Desmos program and I just look up a point, right? I just drag along my cursor until I found a point that was something I wanted to calculate with. So that's the power that you have to solve really ugly pieces of algebra where the numbers aren't nice integers or nice rational numbers even. The power of the computer to help us with graphing, to let us do algebra through graphing. It kind of revolutionized math back in the 1980s when computers started getting powerful enough to do stuff like this. And then, of course, they started making, you can do everything I'm doing right here on one of those graphing calculators that they make the applied students buy. Those of you going on to the AP calculus or AB and BC calculus, they are going to ask you to get one of those graphing calculators because the AP exam demands that you have access to a graphing calculator, and you can't use something that has online capabilities, right? So anyway, there we go. We have a point, we have a curve. Now all we need to know is the slope of the tangent at that point. So that's where we have to use implicit differentiation. Feel free to turn on your mic and ask any questions if you're stuck. If what I'm saying is kind of going over your head, you have any questions, please let me know. Stop and ask. Okay. So we have x cubed plus x squared y. This is how good my memory is. Plus 4y cubed equals 6. All right, so what we need to do is we need to do implicit differentiation on that, because it would be very difficult to isolate that for y. I mean, I can't quite factor y out of all the terms. There's a term there that doesn't have a y. So the best strategy here is not method 1, it's method 2. I'm going to use implicit differentiation. So to differentiate this thing, first I'm going to get, of course, 3x squared. Then for this guy, I'm going to have to use product law. So product law says it's the derivative of the first factor times the second plus the first factor times the derivative of the second factor, and the derivative of the second factor is y primed, plus 4 times, and the derivative of y cubed is y squared times y primed. If you don't like primes, and some of the people who do things more formally tend not to, you could, of course, use dy by dx. It doesn't really matter to me. I'll stick to dy dx this time. I'll do it very formally. Okay, now I can actually start isolating. Remember, my job is, of course, to find the slope, to find the derivative of y with respect to x. So I have to basically now treat this like it's a variable and isolate for it, right? So that's my next step. So I'm going to keep the two terms that have dy dx as a factor on the left side of the equation. And I'm going to move everything else to the other side of the equation. So that's going to be, oh, sorry, I just made a mistake. What's the mistake? What's the derivative of 6? 0. 0. That's better. Sorry about that. Okay, so, oh, and of course, sorry, I moved the other things over, right? So that's going to be negative 3x squared and negative 2xy. There we go. All right, I'm going to factor dy dx out of these first two terms. Then I'm going to divide both sides of the equation by this factor. And that does it. That isolates dy by dx. So this rather nasty looking equation, as weird as it looks, as ugly as it is, actually does represent the slope of that weird diagonal speed bump curve. Everywhere along that curve, the slope is this equation. And I am at the point 1, 1. Okay? So I am going to plug in 1, 1. So the slope is negative 3 times 1 squared minus 2 times 1 all over 1 squared plus 4 times 1 squared, which is, that's going to be negative 3 minus 2 times 1 is minus 2, all over 1 plus 4. So I'm looking at negative 5 over 5, which is negative 1. Let's just take a quick jaunt back and see, does that make sense? If we go back to my graph, yeah, that does kind of make sense. I'm kind of looking at the line right now, or I'm kind of looking at that dot, and I'm thinking the line that would just touch that dot has a slope of negative 1. That does look reasonable to me. Okay, I think that looks good. So let's go back and finish this off. I have a slope of negative 1. I have, oh, you got a question?
I think it should be 12y to the power of 2 instead of 4y to the power of 2.
It should be 12? Where did I goof up? Okay, let's see. 3x squared, check. 2xy plus x squared dy dx. Right? Okay, that's all good.
Check the original equation.
Oh, good heavens. Good eye. Thank you. Who's that? Oh, you don't have to say. I'm recording. Thank you very much, person who's more awake than me. I just, I was up way too late last night. I could not pull my eyes away from what was going on with our neighbors to the south there. My goodness. I finally went to bed around midnight when Pennsylvania had one senator after another getting up and saying they object. Ugh. The other states had the class to say, we object, but we're not going to push our objection after what happened today. Oh, there was one other state that actually made them vote. I can't remember who it was already. But I finally went to bed when Pennsylvania was one senator after another. Ugh, what a bunch of slime balls. Anyway, sorry, didn't mean to get all political on you. So yeah, that should have been a 12. Okay, so what does that change about my answer? You get a 12. And you get a 12. Oops, Oh, that's really ugly. That looks like some sort of bizarre symbol. And you get a 12. And you get a 12. And I'll just recalculate that. No. Okay, so I've got the wrong slope. So the slope, well, the numerator's fine, right? The numerator's negative 5, is that what you got? And the denominator is 13. Anybody else get that for a slope? I actually have an answer. Hang on. I pulled this question from an old book. Oh, actually, the question didn't ask for a tangent line. It just asked for the equation. So let me check. Yeah, I got the right equation. So that has to be the right slope. Okay, so let's finish this off. I have a slope of negative 5/13. I have the point negative, or 1, 1. So y minus 1. I still have some people who goof this step up. Y minus 1. Remember, I'm using the formula y minus y1 equals m times x minus x1. What you learned in grade 10 is called the point slope formula. So y minus 1, that's using this point, equals the slope times x minus 1, which is using that coordinate of the point. So if it doesn't say what form of the equation you want, you could probably just say, there's my equation of the line, I'm done. And you could graph it like that. In fact, why don't we graph it like that? Actually, maybe before this is too much button punching to graph that. Let's make it easier to work with. If it wanted it in slope-intercept form, I'd isolate for y and get rid of the bracket. But most textbooks put their final answer in standard form. So that's what you should be more used to. Now to get to standard form, I still have some people who goof this up. I would times both sides of the equation by 13, which leaves that. And then I would rearrange and get rid of the bracket. So that's going to be 5x, which is negative on this side, so I'd add it to this side. So I have 5x plus 13y. And then negative 5 times negative 1 is 5. But 5 moved to the other side, so that'd be minus 18 equals 0. And this, and I don't know why that just made that weird line, but that's what I'm going to graph. So I'm going to graph 5x plus 13y minus 18 equals 0. So I'm going to go to Desmos, and I'm going to graph, okay, go away. Where's the Desmos thing? There we go. Oh, yeah, but every time I touch the tablet, that happens. 5x, oh, this is such a drag, minus No, it wasn't minus. Now I've forgotten what it was. It was plus, wasn't it? Somebody tell me if I'm punching in the wrong equation, okay? I wonder if there's a way to make this, anybody know if there's a way to make the keyboard not come up? It's probably in the settings. I better not mess with it. Okay, I'll go to here. 13y equals, or no, it wasn't equals. I put this in standard form. And, what was the constant now?
Minus 18.
Thank you. Equals 0. There we go. And this is the whole point of doing that. As you can see, we have a nice little tangent. It looks like a tangent. Beautiful. Okay? Is there a way to actually use the expression, the equation that I got, that big ugly equation for slope, and come up with like a general Desmos formula that I could just put in so I could find the slope anywhere along that curve? Yes, maybe. It's pretty complicated. Okay, I want to do one more problem with you, and literally this is going to be an actual word problem. Okay, can everybody take a look at this? A bicycle has tires with a radius of 35 centimeters. If the bicycle moves forward at a speed of 6 meters per second, at what rate do the tires turn? Now, what you should be thinking here is thinking about x. Okay, go away. I don't know why this is happening. Why won't that go away? I don't know. I can't seem to make that stupid little box go away. Okay, anyways. Whatever. What I want you to think about is, of course, how long that x line is, which is the, there we go, the distance from when this, say, point on the wheel touches the ground to when it touches the ground again. So notice that when the tire turns once, the distance traveled by the bicycle would be what? What would the distance traveled be? Well, it would be the circumference of the wheel, assuming the wheel doesn't slip on the ground. This distance here, that we're calling x, has to be the circumference of the tire. So actually, x is equal to 2 pi r. Hopefully everybody remembers the circumference of the tire. Now that's assuming it only turns once. If x represents a distance where there's a number of wheel turns, then the distance x is 2 pi r times that n, where n equals number of wheel turns. Whoops. Number of wheel turns. Okay, with me so far? So 2 pi rn is really x, and since the radius of the tire is what they tell us is 35 centimeters, then 35 times centimeters, change that to meters, that's 0.35, so 0.35 times 2 is 0.7, so x is equal to 0.7 times pi times n. Everybody get how I've gotten that far? So that equation is true for the distance that the bike goes, assuming again that the wheel doesn't slip or anything. And what I want to know is, if the bicycle moves forward at a speed of 6 meters per second, at what rate do the tires turn? Now, the word rate should be telling you, aha, a number divided by a number, a change in one thing divided by the change in the other. What I want is the change in the x distance over time, which would equal 0.7 times pi times the change in the number of wheel turns over time. This formula involves two different slopes. Slopes are rates, and these rates are related to each other, right? As the number of turns of the wheel increases, the speed increases. As the speed increases, the number of turns in the wheels increase. You can't increase one without increasing the other. So these two rates are related to each other. That's why we actually call these in calculus, and you might have already heard this, those of you taking honors physics, these are called related rate problems. And related rate problems are always going to end up needing implicit differentiation. So, well, the implicit differentiation here is actually really easy because n is just, a single variable. There's nothing fancy about n. So we can say that we actually already know one of these two rates too. Which rate do we know? We know the speed of the bike is 6 kilometers per hour. So the speed, change in distance over change in time, is 6, it's not kilometers per hour, right? It's meters per second. Let me look at my question. Yeah, it's meters per second. So this is 6. And then we can now solve for the change in the number of wheel turns over time, the rate of the turning of the wheels. So that's going to be 6 divided by 0.7 pi. I can run that through my calculator and get that that's around, I've already punched buttons on this. This is 2.73. And that, of course, is number of wheel turns per second. So you'd usually call that revolutions per second. Again, you physics types have seen questions that use revolutions per second, also known as the frequency of the wheel turns, right? That's a really easy version of this problem. Obviously, this step here was just a matter of putting in my ratio, my rate, which is a slope, which is a derivative. Obviously, these problems get more and more complicated when you have to actually do a derivative to get the related rate formula. So we will do some problems like that. If not next week, then probably the week after. We'll get some problems like that going in related rates. And then we're also going to finish the course doing curve sketching. So this is kind of a little sneak peek into kind of the next unit. One other thing I wanted to point out about this problem that I absolutely love is we've looked at all kinds of weird and crazy curves. Yesterday I kind of burned our whole period playing with that lemon skate curve, and I still didn't solve it. I am happy to tell you, last night, while I had C-SPAN on and I was watching the American government implode, I actually did try the problem again, and I totally right away saw what I wasn't seeing. It was a 2-equation, 2 unknown solution. I don't want to burn any more of our valuable class time. We're down to our last 5 minutes here. But if anybody's sticking around because they don't go to music and they actually want to see that 6C problem finished, I totally know how to finish it now. I don't know why I didn't see it yesterday. It was early and I was tired and I hadn't had enough coffee. That's what I'm going to say. Anyway. Like I was saying, we've done lots of problems that involve all kinds of these weird curves, like that lemon skate curve. And isn't there one in your assignment that actually has an asteroid curve? This problem here leads to a curve called a cycloid. We're thinking about this dot as it moves along the ground, but what about what path does it take through space? Like what actual distance in 2 dimensions does this spot on the wheel go in 1 revolution? Well, it actually makes a curve like this, and you're probably thinking, oh, that's just part of a circle. And you know what? You're in good company if you think that. Galileo thought that, but he'd be wrong. Is it part of an ellipse? Nope. It's its own thing. It's called a cycloid. And cycloids and the study of cycloids lead to a problem that's a really famous problem in math called the brachistochrone problem. And brachistochrone is a big fancy Greek word that basically means shortest time. If I put 2 dots on a page, or if I have 2 points in space, obviously the shortest distance between those 2 points is a straight line. Let's pretend I just drew a straight line. But is that the fastest distance? In other words, if this were a plane and I rolled a ball down the plane and I had gravity working for me, is that really the shortest distance to get from point A to point B? Or is there a shorter distance? Or is there I shouldn't say shorter, is there a faster distance? Now, obviously, if you think about A and B, you could do this. You could make a path where, like that, where gravity gets to pull the ball really fast and build up lots of acceleration by gravity, but then, of course, it's going to kind of slow down as it goes that way. Or you could just, again, let it roll down a straight line. Okay, well, I'm going to tell you that this is faster than this. But what's the perfect curve? It's obviously somewhere between these 2 things. And what that curve is, and again, Galileo thought, oh, this is just part of a circle if I keep going. But no, it isn't. It ends up being a cycloid. I'm gonna, for your homework this weekend, if you've caught up on all the stuff that I've assigned, I'm actually not gonna assign anything else new. Tomorrow we're gonna do a little quiz on antiderivatives. And then I'll just let you have the weekend. If there's anything in the other homework that you need to catch up on, you can catch up on it. I'm only going to get you to do one thing. I'm going to get you to watch a video. It's a great video. It's not me talking at you for half an hour. It's by a guy called, the name of the website's called Vsauce. Sorry, it's not a website. It's a YouTube channel. And in this video, he talks about circles and curves, and he eventually has to do some cycloid brachistochrome. And as a bonus, if you were like me, you guys probably grew up watching Mythbusters and are sad that Mythbusters finally got canceled. I don't know so much that it got canceled as they ran out of things to test and got tired of making them, and it wasn't making money anymore. But I miss Mythbusters, and there's a part of the video where the Vsauce guy and Adam Savage from Mythbusters build a brachistochrome demonstrator together, and it's just a delight. And you're not just watching it for fun. We are going to talk about curves like that. It's going to pop up in our next chapter of curve sketching. Okay, that pretty much gets us to the end. It's 8:55. Feel free to log off, you guys who have to head to music, or guys who have had enough of listening to me for the morning. Oh, wait, don't log off yet. Sorry. I haven't printed off my attendance. Hang on. I'm going to print off attendance. This will take me 2 seconds. Don't leave yet. There. Attendance list has been downloaded. So feel free to log off if you need to. If anybody wants to stick around because you've got homework questions, whether it's in antiderivatives or in the other assignments, if anybody wants to see me finish that 6C problem that we were fighting with, we can do that. Okay? So enjoy the rest of your day, everybody. I'm going to turn off the recording of this lesson, and I don't think I won't be able to post it to YouTube until they fix the server, probably. Or maybe I will. I don't know. One way or the other. I'm going to shut the video down. Oh, I got to undo this for that. Oops. And there we go. And okay, recording stops.